Okay, let's start today's seminar. Today, Professor Brett Parker from ANU will give a talk about tropical perspectives on scheme models. Let's welcome.
Okay, thank you very much for inviting me to give a talk. So I took the opportunity to give an abstract on a subject I hope to learn in the meantime. Um, and I still have some, I've been up at night thinking about orientations, and I still have a few doubts about orientations, but the first half of this talk uh, is all done, so all this will be post-rigorous. Um, the second half of the talk may be pre-rigorous, but hopefully still interesting. Okay, so what am I going to do? I'm going to tell you a little bit about tropical curves and holomorphic curves. So holomorphic curves are holomorphic maps of Riemann surfaces into spaces. And tropical curves are like piecewise linear things like this. Um, and then I'll tell you about a three-dimensional tropical correspondence formula. So counting in three complex dimensions, counting three real dimensional tropical curves gives you Gromov-Witten invariants, which count holomorphic curves. And this correspondence formula involves like a quantum deformation of n. So instead of n, I'll have s to the n minus s to the minus n divided by I, where s is e to the I h bar over 2. H bar is like a string coupling constant. And it records like genus of holomorphic curves. And then I'll tell you about how counting curves in a particular type of Calabi-Yau, we see a quantum torus Lie algebra turning up, and you can see that using like this tropical geometry and these tropical curve countings. And the commutator, so it has an element for each pair of each number in vector in Z2 minus 0. And when you commute them, you take this quantum deformation of like the determinant of those two vectors. And the point is to relate this to the Skein algebra, the Hornfly Skein algebra of the thickened torus, where you see a very similar commutation relation, except it differs by this factor of I that's appearing here. Okay, and that's a large source of my staying up at night worrying about orientations. Okay, and the connection is going to be by counting curves with boundary on a Lagrangian, a three-dimensional Lagrangian corresponding where holomorphic curve counts should be valued in the Skein module on that three-dimensional Lagrangian. So I'll say a little bit about how to see tropically the Skein algebra of the thickened torus using these curve counting that I'm talking about. And I'll give you a couple of examples where we can do explicit calculations. Okay. And please jump in and interrupt me. Maybe I'll just meeting chat. Here we go. I'll just have the meeting chat open here. So if you put questions in the chat, hopefully I'll see them. And if I don't see them, just yell out. Okay. So the first thing I want to do is I want to just give you the idea of why these one-dimensional tropical curves come up when you're counting two real dimensional holomorphic curves. So again, a holomorphic curve is a holomorphic map of a Riemann surface into some ambient space. And what I'm doing here is I'm drawing the image of a holomorphic curve in C star squared, okay? And the picture I'm drawing is a log of the absolute value of the coordinates. Okay, so you think of C star as like a great big long cylinder, and we're just looking at the kind of length direction, and this projection here is crunching down the real torus direction. Okay, so what an image of a holomorphic curve looks like is something looking like this. Actually, these edges should be a bit thinner. And these are called amoebas. And what is true is if you look at any piece of the Riemann surface conformally equivalent to a long cylinder, then the holomorphic curve on that long cylinder will closely approximate a kind of a monomial map. So what I mean by a monomial map is you've got a map from an infinitely long cylinder into C star squared, where Z goes to some constant times Z to the A and some constant times Z to the B. Okay, now let's just think for a second, what does that look like when you take log of the absolute value of these things? This actually looks like something, a line traveling in the direction of A and B, okay, of the vector A at B. And the bit that we're not drawing, the bit upstairs in the torus, just looks like a geodesic traveling in the direction of A and B, okay? So what you can do is consider a limit where we scale, imagine kind of zooming out infinitely far. And as we zoom out, maybe change the conformal modulus of these long cylinders and make them proportionally longer. And what we see in a limit like that is called a tropical curve, okay? So it's piecewise linear. It travels in these kind of integral affine directions. And what's more, at each vertex, it satisfies a balancing condition, right? Because you have some cylinder coming in this way, and the direction is determined by the homology class in the torus upstairs, another cylinder coming in this way, another cylinder coming in this way, and these three homology classes here have to add up to zero, and that gives this balancing condition on these tropical curves. There's more general spaces where this works, where you don't necessarily have the balancing condition, but when you're thinking about just curves in C star to the n, then you always have this balancing condition. Okay, so this gives you some idea that, well, you should be able to study holomorphic curves using these tropical curves. And there's McHalkins and separately Siebert and Nishna proved a correspondence formula. And roughly they said that you can count holomorphic curves by counting tropical curves, and perhaps you put some constraints and points to make it pass through some points so that it becomes a count. And the count of the holomorphic curves is given by a weighted count of the tropical curves, where at each of the vertices, the weight is given by the size of the weight of the determinant of two incoming vectors. Okay, so you take two incoming vectors, you take their wedge product, that's going to be something times a times a primitive vector, and that's going to be the weight. Okay. So this works in any dimension for zero genus curves, and in dimension 2, it also works for all curves of all genus. Okay, so what is different in dimension 3 is that for there's a formula that tells you the virtual dimension of the moduli space of holomorphic curves. So and it involves the genus, it involves Chern classes, it involves the dimension of the target space. And in 3 dimensions, 3 complex dimensions, something special happens in that genus doesn't affect the dimension anymore. And it turns out that you need to count curves of all genus at once. Okay. And there's a 3-dimensional tropical correspondence formula I proved a while back to count holomorphic curves. What you do is you do the count that you'd imagine from the old correspondence formula, except you make a quantum deformation of the weight. So before the weight was just an integer n, now it's this quantum deformation of n where s is e to the I h bar over 2. So this is something like this is maybe sine n h bar over 2, or yeah, something like that. Where this h bar records the Euler characteristic of the holomorphic curves that you're counting. So you organize this count of holomorphic curves into a sum where you have the number of curves of a given Euler characteristic, and you weight that by this formal parameter h bar to the power of minus the Euler characteristic. Okay. So the proof of this basically just involves a tropical gluing formula. So you think you've got a tropical curve like this, you have some kind of moduli space from this vertex, some kind of moduli space from this vertex, modeled on holomorphic curves in C star squared in this case, and you glue them over an edge like this. So there's some gluing formula for that, for reconstructing Grove-Witten invariants from tropical curve counts and holomorphic curve invariants at vertices, which works in general. So the proof involves just this tropical gluing formula, but what you can get purely from the gluing formula is just that the invariants are in this form. You can't actually pin down what this S is, okay? And to pin down what the S was, I just looked at a paper of Pundra and for an example to get that S was like this. But any other theory with a similar tropical gluing formula, such as Donaldson-Thomas invariants, will also have a tropical curve count with weights like this, where S will mean something else. So in the case of Donaldson-Thomas invariants, S is q to the half divided by I, where q to the half is just a parameter that is involved in Donaldson-Thomas invariants. Okay, so as a lot of the mystery for me involves comparing this thing here, where I really do need to have the I, to something similar where there's no I in there, you could ask, well, can't we just get rid of the I? And there is one way you can do this. If you count anti-holomorphic maps instead of holomorphic maps, that gives you some kind of sign, which I think maybe for a talk, you can't really concentrate on signs very much. But what effect it has is it kind of changes the gluing formula to now whenever you kind of glue over one of these edges, it changes how you glue by a minus sign. And that allows you to have weights, which are s to the n minus s to the minus n without any I in there. Okay, so that'll be relevant later because tentatively, I think maybe we need to count curves, count anti-holomorphic curves instead of holomorphic curves. Okay, so I just want to talk here about a case where tropical curve counts in a two-dimensional space are a little bit more interesting. So the space is c squared minus this line where z1, z2 is equal to minus 1. Okay. And all right, all of this is kind of post-rigorous. Counting curves in non-compact spaces, how I'm doing it is I have some kind of smooth structure at infinity, which in the algebraic world would be a log structure, just given by a divisor, or I use exploded manifolds. But for understanding what I'm saying today, just think of, okay, we're counting curves in here, and there's something we do when it goes off to infinity to make everything well-defined. Okay, a toric picture of this here. I take this is the toric a toric compactification of c squared, where this is where c squared is. We do this toric compactification of it. We've got this extra hypersurface that we're taking out, and for the log structure, the divisor is this part of the toric boundary divisor and this. Okay, so this is actually a very nice thing. It's a log Calabi-Yau, and it admits a Lagrangian torus fibration. So the pictures I was drawing before had a kind of trivial torus fibration. So the fiber over every point was the imaginary, the circle directions in this C star squared. So this one has a singular Lagrangian torus fibration where over most points there's like a torus fiber, but at one point, this torus fiber degenerates to a sphere that intersects itself once. Okay, so we'll call that a singularity, and that singularity in the Lagrangian fibration, like this point here, is 0, 0 in the complex plane. Okay. So, in fact, because there's this this is a singular Lagrangian torus fibration, like there is an integral affine structure on this space, which the space that I'm drawing, which has a singularity at 0. So it's got monodromy, where kind of straight lines look straight on this side, but I've kind of drawn a blue cut here. Straight lines look like this on this side. Okay. So in this case, the tropical balancing condition holds everywhere apart from at the singularity, where you can have curves coming out this direction or coming out this direction. And this curve that I've drawn here is the holomorphic curve just given by the equation z2 is equal to 0. So perhaps in the picture I was looking at before, that's this holomorphic curve coming here, and it goes off and intersects the boundary divisor there. There's another holomorphic curve kind of going this direction, and that is the holomorphic curve going in this direction. Okay. So maybe just there's one interesting thing here, is that counting holomorphic curves that look like this is very easy. This is just a cylinder, and it's where z2 is equal to a constant, where this constant is much bigger than 1. Okay, but you can consider making that constant smaller and smaller. It moves along this direction until it passes over this singular point where you see, well, it's not allowed to bend like that. The balancing condition has to hold. So you see a holomorphic curve looking like this, okay? And, well, we know to count this one, we need a weight of 1, or maybe a quantum deformation of 1 if we're up 1 dimension. And to cancel that out, you need a weight of 1 over this deformation of 1 here. Okay, so a tropical correspondence formula still holds in this more general setting. In this two-dimensional setting, Pierre Boisseau proved that the quantum deformed weights that I was talking about that apply in the three-dimensional setting count Gromov-Wheaton invariance with lambda class insertions, okay? But I mean, that's equivalent to, in our setting, counting curves in this two-dimensional manifold we're looking at times C star, where you're just restricted to a slice where the C star direction is constant. Okay. So we're going to look at this space times C star to make a three-dimensional thing, but the picture will be, instead of having a singular point, there's now going to be an entire three-dimensional singular line kind of passing in the direction perpendicular to the plane that I'm drawing. Okay. So now I want to talk about the three-dimensional situation where I can take C3 minus this divisor, which is very similar to the one that we looked at. And that also has a singular Lagrangian torus vibration, except now it's got a singular locus, which is over these three lines that I'm drawing here. And counting, so this singular locus, basically, it happens where 2 of Z1, Z2, or Z3 are equal to 0. So this point is where Z1, Z2, Z3 are all 0, and where 2 of them are equal to 0, we get these other singular bits. And all of that lies in the plane where I guess Z1, Z2, Z3 is equal to 0. And counting holomorphic curves within that plane, there's basically interesting holomorphic curves that kind of come in this direction, interact here, and come out like that. And the Gromov-Witten invariants counting these things compute the topological vertex of Eigenargy, Clem, Marino, and Buffer. So with norm dou, we proved that there's a quantum torus Lie algebra acting on these Gromov-Witten invariants, acting on the topological vertex. And the quantum torus Lie algebra has generators, one generator for each integral, non-zero integral vector in this plane. So there's going to be vectors like that. And this commutation relation involving the determinant of V and W, this quantum deformation of it. So where this quantum deformation, again, has this factor of I in it, which is different from but very close to the Skein algebra for the thickened torus. Okay. So how do we prove this? Well, each of these legs here is modeled on this thing that I was talking about up here times C star, so times a third direction. So we have the Gromov-Witten invariant. There's interesting Gromov-Witten invariants that kind of come along here and count holomorphic curves where one leg of the curves comes in direction V, and you've got some incoming curves, some outcoming curves, and we can package these Gromov-Witten invariants into operators, TV, and these operators satisfy a commutation relation, which is a central extension of the quantum torus Lie algebra I was talking about, but I won't say anything about that. But the commutation relation is really easy to see tropically. So what you do, you compute TV composed with TW, maybe where the operation that operates going incoming this way and outgoing that way. TV composed with the TW, you count Gromov-Witten invariants, maybe where you constrain these legs to pass through points out here. But the thing is, these Gromov-Witten invariants, they don't depend, they're deformation invariant, so we can just move where these constraints are to this situation where you've got the constraints swapping the order in which the W and V operators act. But there are extra types of holomorphic curves in this situation where V and W come together, they interact, and then come out using the balancing condition with in direction V plus W, okay? And we know how to count the contribution of these holomorphic curves is just this quantum deformation of V wedge W, the size of V wedge W. Okay. So this just kind of follows from this tropical gluing formula and the tropical correspondence formula for this three-dimensional setting. Okay, so I'll just say one little technical thing. A priori, there exist holomorphic curves and tropical curves which look like this, where you've got maybe some a loop in here. Okay, and these holomorphic curves exist, but you can perturb them away, basically because everything here is confined to this wall where z1, z2 is equal to 0. When you go and apply the gluing formula, and you glue first, come around here, and you try and glue again, then the intersection is 0. So you can make sure that curves like that don't count, and the only thing that counts is this. Okay, so that's I don't know. I think that's nice that you kind of see this commutation relation using tropical curves counting. Okay, we're going to do the same thing for the Skein algebra of the thickened torus. And to do that, what we need to do is use the formalism developed by Ekholm and Schinder. So the setup is you're in a Calabi-Yau threefold. Okay, so it's a three complex dimensional manifold, and it's got a non-vanishing holomorphic volume. And you're counting curves with boundary on a special Lagrangian in X, or more generally a Maslov zero Lagrangian. So special Lagrangian means this holomorphic volume form is real on all of on the tangent space of this Lagrangian sitting in here. Okay, so Ekholm and Schinder tell us that to count holomorphic curves and get something invariant, then what you need to do is you have to have counts taking values in a Skein module on this Lagrangian. So one technical thing is that you need to count bare holomorphic curves, which roughly means that you could have for Gromov-Witten invariance, you've got to count holomorphic curves, nodal holomorphic curves, possibly with some components which are mapped entirely to a point. And bare curves, you don't count those things. Okay, so the reason but I want to count using Gromov-Witten type of counting where those do count, basically because these bare curves, I don't know how to prove a gluing formula for them, so a tropical gluing formula, because like there are certain arguments, compactist arguments, where you say, well, you don't get these these contracted components in limits, so we can kind of not look at them, and those don't actually work in the exploded manifold setting, or the setting you need to prove the gluing formula. So what I want to do is instead count Gromov-Witten invariance, and in the case of, and roughly speaking, the relationship between Gromov-Witten invariance and the bare curve count should be that you put the bare curve count has this parameter z, and you replace it with this quantum deformation of 1. Or when you're talking about anti-holomorphic counts of curves, then you can replace z by this other quantum deformation of 1. So what I want to do is to try and use try and get the formulas to work for Gromov-Witten style counts. And what I'm going to talk about is, not the setting where where everything is proved, but in the log Calabi-Yau, well, because there's very easy examples. So a log Calabi-Yau example would be C star cubed. The holomorphic volume form is just, the C star cubed invariant thing that you'd write down. And an example of a special Lagrangian, I could take the real circle in the first 2 coordinates and a positive real line in the 3rd coordinate. So that's easy to check. This is a special Lagrangian. Okay, so the advantage of allowing yourself to work in log Calabi-Yau things is there's lots of very easy examples. The disadvantage is that Baire curve counts are not defined in general. So there's special, there's some cases where you can define Baire curve counts, but in general, it doesn't work. So let's see. Okay, so what you need to do is you need to have this Lagrangian, need to choose a spin structure on the Lagrangian so you know how to orient things. And then you count holomorphic curves of this, and these take invariant values in something called the worldsheet Skein module, developed by these people. And then what you can do by choosing extra data, you can map this worldsheet Skein module to the Homefly Skein module. Okay. So, all right, maybe I'll just briefly say, okay. So the Homefly Skein module, that's oriented framed links in your manifold up to isotopy, and these 3 Skein relations where exchanging a positive crossing for a negative crossing gives you S minus S inverse times what you get by resolving this crossing. And the unknot is equal to A minus A inverse divided by S minus S inverse, where A is a parameter that keeps track of framing. So changing the framing by a positive twist multiplies your framed knot by this parameter A. Okay, so I think possibly for this audience, you all know much more about this Skein module than I do. So the worldsheet Skein module is a bit like this. So the worldsheet Skein module is isotopy classes of embedded Riemann surfaces in the ambient manifold X with boundary on the Lagrangian L, which are holomorphic near the boundary and which also don't intersect L in their interior. Okay, so you've got those things, you've got isotopies of those things. And one thing that could happen in an isotopy is that well, in this case, a negative crossing crosses over and changes to a positive crossing. And in the middle, they have this kind of intersection point. And how you kind of resolve that on the boundary, you just resolve how you resolve in the usual Skein algebra, but that corresponds to kind of taking two components of the holomorphic curve and gluing them at that intersection point. Okay. So now there are, I think, two types of Skein relations corresponding to these crossings in this worldsheet Skein module, and we need to kind of distinguish between them. So one of them, when you resolve it, you get something connected, so some connected link, connected knot. And the other one, when you resolve it, you get something disconnected. Okay, and so what? So why do we need something like this to get invariant counts of curves? It's because okay, this connected hyperbolic case, what can happen is you can have a holomorphic curve, maybe holomorphic curve. Here's a holomorphic curve. Here's the boundary of the holomorphic curve, and I'll make it look something like that. What can happen is that a bubble can form, a boundary bubble can kind of form a node, can form on the boundary, and this is a boundary of the moduli space of these holomorphic curves. So it's codimension 1. It's a boundary, which is bad if you want invariance. Okay, but what this is saying is that if you look at the moduli space, you've got kind of these resolved things. They come down here, and then you've got the boundary. And this is saying, well, you can cancel out that boundary using this Skein relation here. Okay, so I've been spending quite a few sleepless nights thinking about exactly what the signs need to be to make everything work out. But I'm sure you don't want to see me do that. I'll just say that the signs of these in these Skein modules, Skein module relations, tell you something about the relative orientation of like this glued moduli space here compared to these unglued ones. Okay, so changing, and in this case, I think the holomorphic convention gives one relationship between the orientations like this, and the anti-holomorphic convention gives a different relationship between the orientations like this. And somehow, for invariant counts of curves, it's very important that all the orientations are correct. Okay, so the thing is that how you get orientations in the moduli space of holomorphic curves is you kind of take your curve. It's got some kind of you want to orient the linearization of the d-bar operator for this curve. Okay, but it's not clear how to do that. It's clear how to do it for closed curves with no boundary, because you just take a homotopy to a complex linear map, and that gives you a canonical orientation. In this case, what you do is you kind of deform the domain until you have like a disk with a boundary and glued to a holomorphic curve, a closed holomorphic curve. And then you take this disk with a boundary and you deform the d-bar to a particular model problem depending on the spin structure on your Lagrangian. Okay, and this kind of argument, there's two different models that you get for depending whether you have a connected hyperbolic crossing like this or a disconnected hyperbolic crossing like this. So a priori, the signs might be different in these. Okay. There's another Skein relation, which on this right-hand side, we're considering a boundary of a moduli space where you've got a holomorphic curve with boundary, and the boundary kind of shrinks a little until you just get a point. And that is another one of these, codimension one bad boundaries in the moduli space, which we need to get rid of. And this is this is cancelled out by something in the Skein relation where you've got a family of holomorphic curves not intersecting L. In the middle, the not drawn thing, this intersects L, and on this right-hand side, it's kind of passed to the other side of L. Okay, so somehow you've got a one-dimensional family of these which intersect L in a positive or negative sign, which determines the sign here. So you also need this kind of elliptic Skein relation. Okay, and the disconnected hyperbolic and elliptic Skein relation, the signs of those are kind of fixed fixed relative to each other, because you've got a kind of cusp family of curves where you've got this on this end, that's an elliptic singularity, and on this end, it's a disconnected hyperbolic singularity. Yeah, because we're disconnected hyperbolic, because when we resolve it, we get these two things. Okay. So the point, so we need to relate these two Skein modules. Like a priori, it's not obvious that a world sheet Skein module like this is non-trivial, but there's a way of mapping the world sheet Skein module to the Humphrey Skein module using extra data. Okay, so what you need to do is you need to choose a nowhere vanishing vector field V on your Lagrangian, and then also a 4-chain with boundary which is 2 times the Lagrangian L. But this 4-chain has to have a special form close to the Lagrangian, it needs to look close to the Lagrangian, like the Lagrangian pushed off in two different directions, which are, you take this vector field V on the Lagrangian, and then you can twist it using the complex structure to a vector field in this direction, or take minus it twisted by the complex structure to something in this direction, and you've got the two push-offs like that. Okay, so once you choose this data, then the map from the worldsheet Skein module to the on-fly Skein module is just given by this framing factor A to the power of the intersection of your holomorphic curve with C. So C is a 4-chain. Your curve is 2-dimensional. This will have some intersection number, which you can put in here. And that kind of accounts for the framing. And you have this this parameter S minus S inverse to the power of minus the Euler characteristic of your curve, and you multiply that by here the boundary of the curve gives you an oriented link, and using this vector field V, you get a framing for that link. Okay, so there's some way of taking this extra data and getting something in the Skein module. Okay, so I'm going to suggest that. So this is something that you use for Baire curves, but to relate Baire curves to Gromov-Witten invariance, the Baire curve count I can replace with that anti-holomorphic Gromov-Witten count, where S is e to the lambda over 2, where lambda is the string coupling constant in this case. And there is a Gromov-Witten alternative where you take Z to the power of this minus Euler characteristic, where Z is I times S minus S inverse. But to compare to like known results on Skein modules, I want S minus S inverse rather than I times S minus S inverse.
Sorry, Brett,
Yeah.
I have a question for you. So when you write this Gromov-Witten invariant, what do you mean then? It's the Gromov-Witten invariant of closed curve, open curve, curve with ray boundary, or what kind
Yeah,
of?
so it's so this is so this, as Tobias is perhaps noticing, is something where the technical details have not been written. So this is meant to be Gromov-Witten style count, so count of stable maps with boundary on the Lagrangian. And the reason I want to do that is because these can easily be computed in the examples I'm thinking of.
I see, but that would mean it's with respect to some bounding cochain or some kind of system like that. I mean, it's some kind of involved count, right? It's not, yeah.
So in this case, all right.
You have to cure some wall crossing, right?
Yes. So we can discuss this later.
Sure. Yeah.
Yeah.
That's okay.
Yeah. So it may be this doesn't work. Sorry. But the examples are encouraging. Okay, so let's do this thickened torus example. So in this case, the ambient log Calabi-Yau is just C star cubed. Okay, so tropical curves are going to be easy to draw. The Lagrangian is a circle in the first two components times a line in the third component. Okay, so when I draw this, the Lagrangian is just going to be a line where I'm drawing this third line component, and I'm not seeing the two real torus components here. Okay, so in this case, there are some very easy holomorphic curves, which are just half cylinders, which are just monomial maps. Okay. Now, so you have a monomial map that goes minus a in the first direction. The boundary of this goes a times around the first direction and b times around the second direction. Okay, so you know what knot this represents. Just a knot in the direction AB. And you can write down explicitly what the entire moduli space is. But what's especially nice about this moduli of half cylinders is that this method for orienting moduli spaces, like, deforms things to a standard problem. The linearization of the d-bar equation for these ones is that standard problem. Okay, so the moduli space is very easy to orient here. Okay, so I've just written down the rule for the orientation, but the simple rule, this tripped me up for a while. The simple rule is for the spin structure on this Lagrangian given by the obvious trivialization of the torus times the trivialization in the r direction. So, you know, these three coordinates, theta 1, theta 2, theta t, give a spin structure, and it's going to be relevant that this spin structure doesn't extend when we kind of fill in to get the solid torus. Okay, so the point is, these are very easy to orient. Okay, so let's see. The Skein algebra of the thickened torus is worked out by Morton and Samuelson, and it's beautiful. So it's an algebra because you can multiply links just by kind of stacking them like that. Okay. And the generators of this Skein algebra are just exactly the curves that we get as the boundaries of these half cylinders. And the relations are the commutation relation just uses this quantum deformation of the determinant of V and W. So, like what I get in Gromov-Witten worlds, but differing by a factor of I. Okay. So let's see. Can we see a Skein relation like this using holomorphic curve counts. So here, all right, so you should think maybe this this Lagrangian line I'm drawing is going in the third direction, kind of up out of the plane, perhaps. And we've got these holomorphic cylinders, V and W, with boundary the corresponding generators PV and PW of the Skein algebra. And well, to get the commutation relation, we just consider this moduli space where half of the moduli space has V on top of W, positive crossing. Half of the moduli space has W on top of V, that's the negative crossing. So the Skein relation says that this minus this should be equal to the kind of resolved thing. And the resolved thing, we can also work out exactly what the holomorphic curves are once we kind of take these two, these in the middle, we've got these two half cylinders intersect, and we can glue them together into a moduli space looking like this. And we can write down what this moduli space is. And we can also orient it, because what we can do is we could, once this is long, we know how to orient this this cylinder here, just using the same method we used to orient these. And it's glued to something out here where we know what the orientations are from, because it's a closed curve. So modeled on closed curve here, okay? So again, this is in the standard form where you can just write down what the orientation is. Doesn't mean I didn't make like 3 or 4 errors while doing it, but it is possible to do that rigorously and explicitly. Okay, so for counting, so what seems to match up? There are ways to make counting holomorphic curves and anti-holomorphic curves match up for just this this kind of Skein relations. And the count of the holomorphic curves out here is weighted by this factor, the size of the determinant of V and W, the quantum deformation of that, using the anti-holomorphic conventions, which is just s to the n minus s to the minus n. Okay, so we get this. The sign you get here depends on the orientation of the moduli spaces, which kind of depends on depends on this sign of V wedge W. So that works out. And what you get is something which matches the commutation relation we expect in the Skein algebra. Okay, so this, I should say that if V wedge W is 1, then these curves are embedded and you can do Baire counts and everything is good. If V wedge W is not equal to 1, these curves aren't embedded, and the Baire counts, let's call it, is heuristic. I'm guessing what the Baire count should be from the Gromov-Witten count, So for example, where it's 3, what I expect for anti-holomorphic, as in the opposite of holomorphic. Anyway, so the count of curves that you see here would have 3 genus 0 curves, but kind of when you look at the curves that are there, they kind of intersect each other themselves 3 times, and you get a higher genus curve in there as well. All right, so I just wanted to say that so I could do rigorous counts in some cases, but other cases use some kind of theory that works for like stable maps instead of bare curves. Okay, so all right, this is just about the orientation. Let's consider now the example of the solid torus. Okay, and this is in this manifold that we saw before when we were talking about this big quantum torus. So the manifold that we're looking at is C squared minus this divisor times C star. And the tropical picture of this has this kind of singular locus traveling along here. So elsewhere, the fibers over what we're drawing, this is 3-dimensional picture. Elsewhere, fibers are 3-dimensional real tori. One direction in, over here, it looks like a circle times a sphere that intersects itself once over this singular locus. Okay. And I can draw a nice Lagrangian in here, where in the C squared direction, it's just the first component is the complex conjugate of the second component. So these, I think, are called eigenargic Waffer branes. So they come in the story of the topological vertex. And in the third direction, so that's the direction this way, it's just a circle. So everything is kind of the circle direction paired with this. It's kind of it's symmetric in that direction. Okay. So in this case, in the previous case, this chain bounding L that didn't play any role. But in this case, we need to consider this chain bounding L. And what I can do is I can just push L in this third direction. So this direction is the direction of the real direction in C star. So we can push it in one way and push it in another way. Okay. So just to orient where this is. So the pictures that I was drawing before involved kind of holomorphic curves, kind of there's some holomorphic curves that end on this singular locus, and these are perpendicular to this Lagrangian here. Okay, so well, here is the holomorphic curves in question. There's these holomorphic curves that come and just end on the Lagrangian. Okay, and you can work out, this one intersects C positively. The one on this side intersects C negatively, and kind of in this family, they intersect L here. So this is like a skein, where one of the worldsheet skein relations happens. And you also have, okay, so this kind of coming in here perpendicularly, there are curves, half cylinders that we were looking at before that come and end perpendicularly on L. And these are just exactly the half cylinders that we were studying before, we're seeing before, okay? So somehow this kind of, you've got the Skein, the Skein algebra on L involves like curves kind of ending on here and stacking these. And what you can do is you can kind of take these and in the modulo space you can bring them down and move them out to here, or here, and you can get the curves that I was talking about when I was talking about the quantum torus Lie algebra acting. Okay. Okay, and in this Skein relation, to the counter of these curves involves 1 over this quantum deformation of 1, that anti-holomorphic version, because I think that's what works. This one involves the, okay, so the Skein relation says count them like this with a minus sign here and equate it to the what you get counting over here, where this is just this bounds a curve, which is the unknot up here. And this quantum deformation of 1 is just 1 over S minus S inverse. So we see this kind of Homfly Skein relation where the unknot is given this value here. Okay, and this works up to sign. So I should just say that orientations, these ones are just holomorphic or anti-holomorphic curves. Orientation, very easy to work out explicitly. These ones are the half cylinders, and again, orientation is very easy to work out explicitly, but you need to be careful in that the spin structure, like the spin structure that we were using before, is like given by trivialization, which kind of goes around in this circle direction. And that, when you compare it to the spin structure that extends all the way to the disks, so the only spin structure you can have around the unknot, this one is the opposite spin structure. Okay, and when you work out the orientations, changing the spin structure on a boundary loop just changes the orientation by a sign of -1. So that gives you a correction sign to work out what the orientation should be in this case here. And again, somehow, I'm writing like counts of stable maps because that's what I've got the technology for working out what this thing is. And these are all embedded curves, and the bare count is the same as the stable map count, what is suggested by the stable map count in this case. So what it looks like is that as long as the orientations work out, there's this kind of nice calculus, tropical calculus, of how you calculate the Skein valued holomorphic curve invariance here. And they can give you, well, I mean, it's kind of, I think, cool that you see this kind of Skein relation, the Skein algebra relation, using these kind of counts of tropical curves, which kind of rhyme very much with the counts, the calculations that I was doing with norm dou in the case where we don't have boundary. And the similar technicality, that curves looking like this with kind of two things attached to L, they exist, but they can also be perturbed away in this case, just like in the case of the topological vertex that I was talking about before. Yes, so I think, yeah, I use preparing this talk as an opportunity to try and get orientations completely straight in my mind. I'm not 100% sure that everything is completely straight in my mind yet. So, so what I've given you is some examples where we can really pin down the signs, what the signs have to be in the worldsheet Skein module, because everything can be done really explicitly. I've been using counts from Gromov-Witten invariants because those I know have gluing formula, but the technicalities for actually defining Skein valued counts of them may well have problems that make things never work. But this is kind of indicative that perhaps something does work. So I think I'll end here and maybe take questions.
Thank you very much for interesting talk. Are there any questions or comments?
Yes, I have a question, a comment. I mean, I have a comment. So maybe if we look at this picture that you have, I mean, this kind of V and W, and when you swap them on the right side of this screen share, so I think from kind of Skein perspective, so if we start with the case when these curves are actually embedded, and maybe there are many. It's not just one Skein relation; it's many Skein relations. So this formula holds, and what you give is sort of special nice proof for a special complex structure, let's say. So you somehow find some curves, and then on the left-hand side, maybe in the simplest case, everybody is bare.
Yeah.
And then on the right-hand side, you have a collection of curves with maybe it could perturb to bare, not bare, but you push all the holomorphic interesting stuff into this vertex in the middle, right? And
Yeah. So
when
basically
you do the Skein count, you don't
yeah.
have to do that. It could be that some stuff survives in some strange knot theory on the boundary, but you have a nice way in this tropical limit to somehow control where things go.
Yeah. Yeah,
And
that's right.
and another comment in this example is that by some kind of indirect methods with curves at infinity and so on, we can compute the contribution in the Skein even of the multiply covered V and Ws. Uh,
Yeah. So
and
somehow I should just say the multiply covered V and W's this gluing formula here also works when there's multiply covered here. But then I'm very far from being able to say exactly what their curves are, because I think it's likely that the relationship between bare curves and Gromov-Wheaton invariance is what you expect from a closed case when each of these things is a primitive, so singly covered. But in the multiple covered case, I think stuff goes wrong.
it's more interesting. But what I want to say is that whatever kind of thing we say, if we say we know this curve, what's the contribution of multiply covered thing? The only way we know it is in this Skein module. So we cannot say that, you know, this and that comes from here and there. But I think in this, what you're in this, when you have all these nice things, you can probably make sense out of this kind of
Yeah.
with certain representation. But in our work, I think all of what you're saying, I mean, say for this sign, which we discussed back and forth, but which possible to somehow, whether it's holomorphic, anti-holomorphic, it's possible probably to make agree with our sign. I think everything what you're saying perfectly consistent with this Skein counting, and it seems like this tropical picture gives you a very nice way of actually pushing genus contributions around in a more controlled way than these general perturbations for bare curves, right?
Yeah. So somehow I mean, what is nice about this tropical counting is that everything can be made pretty explicit, but
Yeah.
what is difficult for the Skein valued counts. So certainly in other cases that I've been thinking about is the Skein valued counts. What we want is generic, and somehow the nice cases, nothing is generic almost.
That's right.
So yeah, I mean, I've heard it, be described as the problem of looking for hay in a haystack, trying to find, something that's non-generic, and that certainly holds in the case of trying to count curves.
Yeah. Yeah. Anyway, it's very nice. So thanks for this talk.
I have a comment and some questions also.
Yeah.
So the comment is that maybe just to sharpen Tobias' comment, the point is that I think what Tobias was saying is that in our work we have proved more relations than just these Skein relations by some roundabout kind of argument. So what Tobias was saying was that this kind of relation between curves which look multiply covered, we have proved that relation.
Yeah.
So we've proved it also holds. And the proof's some complicated thing where we perturb things and then make some indirect argument and so on. Um, which is to say that you could imagine uh, if you imagine trying to prove that this kind of tropical curve count respects Skein relations or whatever, it is known that the Skein valued curve counting has certain behavior for multiply covered curves. That's what Tobias is saying.
Yeah.
E-
Yeah. I mean, so,
Even though those curves are not by definition allowed in our subject.
yeah. Yeah. I mean, somehow, I think once you have like this, this is I think there's a separate way of seeing that by comparing like algebras that you have. Like somehow you've got some kind of algebra over here which is generated by stuff which is just embedded. And similarly, um, in this Morton and Samuelson business, the generators that are obvious are just are not everything, because if you have a non-primitive vector that corresponds to something going around n times. But I think just kind of by comparing the two kind of algebras, like the algebra from here and the algebra from Morton and Samuelson, you can just get that if you have an n-fold cover, at least in a limit like this, then it's just the power sum thingy. So there's given a knot, there's some kind of canonical knot, which is like the what you get from an n-fold cover of that, which is just I think this paper has like a explicit representation of it or something, right?
Yep. So I also have some questions. One is, are you always in the situation where the curves all lie in some plane?
So the theory works generally, but to get tractable tropical curve counts, it is extremely helpful if things are forced to lie in a plane, because it kind of eliminates the combinatorics of trying to find all the higher genus tropical curves, which is non-trivial. So, I mean, let's see this example, I mean, this is three-dimensional, like L is going up from the plane and V and W are kind of out from the plane. But, what kind of saves things a bit is like the directions that we have, this individual tropical curve is just in this plane. So yeah, I mean, all the ones I've drawn here are just tropical curves living in planes, but the tropical gluing formula works in general. It's just harder once crazy genus can happen.
Yeah. And why is this worldsheet Skein relevant to anything?
Okay, so what I like about the worldsheet Skein is that it's completely canonical. So
But not as a philosophical matter. If I hate the worldsheet Skein, do I need to learn it, or is it somehow is it just so you want to think about it that way?
All right. So for the route I'm taking through this, I'm trying to understand science. Okay. And the worldsheet Skein, I can calculate the orientations of moduli spaces. The worldsheet Skein says, what's the relative orientations the worldsheet skein says how those orientations are related. Okay, and that's kind of, part of the problem is this, going from holomorphic stuff to orientation. So that goes to worldsheet skein, and then like there's this second step, which once you're in the worldsheet skein module, going to the Homefly skein module, that's just topology now. So somehow, this is some kind of topological thing. Once I fix these signs, it determines what you need to go
In
to.
other words, the reason you're doing it is because you're trying to track down some sign, and so you're trying to do as little operations as possible until you get to the place where you see a sign. That's so
Yeah.
you don't want to go all the way to this Homfleet thing because then there's more numbers involved, and you want kind of less
Yes.
numbers.
Yeah, so more numbers. I mean, and also just somehow there's like the data you need to go from the worldsheet skein module to the Homefly skein module. In many examples I've been interested in, I just find it a bit more difficult to get that data and have it kind of act naturally.
You don't want to choose this for chain and vector field and all that stuff.
Yes, and certainly it kind of like in the examples I'm looking at, the 4 chain is a bit dodgy. It kind of goes off to infinity, so I need to worry about do the boundary of curves cross it and stuff like that. So somehow what I feel is that like saying the count of Baire curves take invariant value in the worldsheet skein module is universally true, and then to get kind of useful comparisons to something in the Homefly skein module, we need to choose this extra data to go over here. So somehow, I think the most natural thing is to go from your counts to the worldsheet skein module, and then choose your data to go over to here, I think. But also, I mean, part of the reason I'm tracking down these orientations is just, it seems very close to working with these Gromov-Witten counts, but, orientations are difficult. So I just wanted to, pin them down as well as I can.
And actually, I have one last question: is why do you say that this Baire counting doesn't work in this log Calabi-Yau world?
Yeah. Okay. So I think there's this. You prove some kind of like it involves a compactness thing where you say that somehow generically you can get rid of most of the ghost components.
Yeah.
But the thing is that always in, say, the log Calabi-Yau world, you go to the divisor and you have like multiple covers in that divisor, going to that divisor or asymptotically, and you just can't get rid of the ghost.
No, maybe I don't understand. So, is the point that when you say log, you don't you don't permit yourself to perturb at the log divisor?
You're permitted to perturb at the log divisor, but I'm pretty sure that it would be a perturbation that's quite different from what you naturally use within log geometry or exploded manifolds. But what I think, I tried to go through that argument, and I couldn't make it work in this setting with the divisor.
But you couldn't make it work for the reason that you don't know a perturbation which destroys multiple covers.
Yeah, so perturbation that's more than destroying multiple covers. You need to like, there's this stage where there's like you have this perturbation, you need kind of compactness. I think compactness is the extra thing you
No,
need.
but multiply covered ray orbits are okay, right? It's the boundary that's okay. Of course, maybe not exactly what we wrote, but those are
No,
more
no,
like.
no. Tobias, what he's saying is that in whatever he's doing, so in our argument, we need first to make the curves not multiply covered. I mean, what you're saying is correct, but we need to first make the curves not multiply covered before we run the ghost bubble censorship argument. And so what I think that Brett is saying is that he doesn't know the name of a perturbation, which will force every kind of a curve without ghost components to be not multiply covered,
Oh, yeah.
and then he can't run the rest of the argument. That's
I
my
see.
understanding.
But that's, I mean,
Maybe it's just a failure of me.
no, but
No, no,
no,
but before we try and fix that, is that what you're saying? Is that the nature of the problem?
Oh, well, so yeah, so I mean what I want is a theory that I can, confidently apply tropical gluing formulas to. And the Bear counts, I'm not so confident.
No, no, no. That's some separate question. You first made a statement about having nothing to do with tropical geometry, about this bear counting not working in the log Calabi-Yau world. And that
Yeah.
statement, I mean, that statement has nothing to do with tropical geometry. And the reason you were saying that was true, I thought, was that there's some degeneration where you cannot, I mean, how to say, there's some place where you cannot prevent multiple covers from happening. Is that a correct description of the problem?
I'm not pro- so somehow, the compactness issue you need to think about is you could have like ghost components appear,
Mm,
and you need to prove that that has high enough codimension or something like that, I think.
that's right.
And that's the bit I couldn't do. Now, basically, being able to prove in the log in the log setting, going from defining it in the log setting to proving a tropical gluing formula is once you've defined once you can make the argument work, that should be trivial.
What I don't understand is what is different in the log setting about this codimension argument.
Um,
Because
so,
wherever the ghost component is forming, it forms in some particular. I didn't know this exploded, whatever. But if it's like this kind of old rubber story,
yeah.
the ghost component forms at some particular place,
Mhm.
and so I don't understand why it's relevant whether you're in the rubber or not in the rubber or whatever.
So it might just be so going so somehow when you've got um, uh, when you've got somehow like the the let's call it the rubber direction.
Mhm.
Um, so the formalism that I have, like there's limited perturbations you can do kind of in this somehow you think of the rubber as like a C star times something, okay?
Mhm.
And to make things work out, it's you, almost always. I mean, the way I've done things is I need to have things invariant in the C star direction.
Yeah, I see. So your
That
perturbations
doesn't.
have to be C star invariant. That's the issue. and therefore you can't eliminate certain multiple covers, and therefore you can't run the skilled bubble argument.
Yeah, and maybe that's fixable, but
Sure, but that's the nature of the difficulty.
yeah, I think so.
Okay,
It
great.
might just be my failure to do it.
No, I don't think so. I think you have to break such symmetries in order to. I think it's very hard. I mean, if you try to basically keep some two-dimensional thing invariant, I mean, it's very hard to make boundaries embedded and so on. So maybe you have to break the symmetry to go to this bear curve count.
Yeah, I mean, I certainly couldn't work out how to.
Yeah, sure.
Okay, thank you very much. And then let us thanks to the speaker again. Thank you very much. And let's finish today's seminar. Thank you very much for your interesting talk, Brett.
Okay.